Hello, everyone. Today, we are very happy to have Masanori Hanada from the University of Surrey, and he's going to tell us about the deconfinement transition in the D0-brane matrix model. Go ahead, Masanori.
Okay, thank you very much for the invitation. Today, I want to talk about the confinement, deconfinement transition in D0-brane matrix model. And the confinement phase, which wasn't known before, I think, is I want to convince you that that can be a good evidence that this model can describe M theory. D0-brane matrix model, which is often called the BFSS matrix model, is this is a Lagrangian, and this is a dimensional reduction of four-dimensional maximally supersymmetric YAMLs to 0 plus 1 dimension. There are 9 bosonic matrices, bosonic n by n Hamish matrices. This is M, and M prime runs from 1 to 9, which correspond to 9 spatial dimension string theory, roughly speaking. And there are 16 fermions. This alpha and beta runs from 1 to 16, and that is related to number of supersymmetry. And each of X and psi are n by n matrices. This model was proposed in 1988 as a matrix regularization of supermembrane in 11 dimension in light cone gauge by Dwight, Hooft, and Nicolai. At the time, these people tried to interpret this matrix model as a first quantization of supermembrane. But then soon, Dwight, Fischler, and Nicolai noticed that there's a flat direction in this model. So here, potential is commutator squared. So if matrices are simultaneously diagonalizable, then eigenvalue can take large value without costing energy. And with the supersymmetry, that flat direction survives only even in quantum level. So bound state of eigenvalue is unstable. And they wanted to understand the sort of the bound state of eigenvalue as a membrane. So they thought this may be a sick theory. But in 1996, somewhat different context, Banks, Fischler, Schenker, and Susskind, BFSS, proposed that this model might be a non-perturbative formulation of M theory. And from a supermembrane point of view, then that flat direction would mean not just one membrane, but some eigenvalue escape. That would mean one membrane or graviton is emitted from this object. And 2 objects, 3 objects, much from object can be described in this theory. If you interpret it that way, so rather than the first quantization, we can interpret this model as the second quantization of membrane theory. Then flat direction is a feature rather than a bug. And off-diagonal entries are connecting to different blocks, diagonal blocks, seems to give a gravitational interaction. So these people propose that this model can be non-perturbative formulation of M theory in some gauge. And after that, Itzhaki, Maldacena, and Sonnenschein, and Yankirovich looked at this model from the viewpoint of Maldacena type duality, and they considered the Hooft limit, which is different from a parameter region these people consider, and proposed that in near to Hooft limit, type 2A superstring can be described, like in ADS5 CFT correspondence. It's very similar, though it's not conformal theory. And based on BFSS proposal and several papers appeared after BFSS, these people speculated that then this model would describe both type 2A and M theory and the parameter region in between. And in this talk, first I want to show that the deconfinement phase of this D0-brane matrix model agree very well with the type 2A superstring. And I will give you a very precise test by studying the D0-brane matrix model using a Monte Carlo simulation. And I want to convince you that the agreement between the confined phase of this theory and the type 2A string is very good. But if type 2A corresponds to the confined theory, in order to go to M theory, we need some different phase. And in the second part, I want to convince you that the confinement phase can be good candidate for having the M theory dual. this part is somewhat speculative, and I cannot give you a very precise argument, but hopefully I can convince you to some extent. And then I argue that if M theory is actually described by this theory, we should better have a confinement phase. Okay, it's not does not follow from M type 2A. We need M theory to have a confinement phase. And we actually show that such phase exists. We can do numerical simulation and we can find such confinement phase explicitly. So let's start with the type 2A region. So Itsuki and the collaborators said that the P plus 1 dimensional YAMLs, which describes a bound state of DP branes and the strings connecting them, is dual to black P brane in type 2A or 2B string theory. And when P is 3, ADS5 D3 brane geometry is nothing but the ADS5 cross S5 if you go near horizon. So this is just ADS5 CFT for correspondence. But from a QFT point of view, this P is spatial dimension, and the spatial dimension 0 or 1 or 2 are totally well-defined QFT. And by using such well-defined QFT, we can non-perturbatively define type 2A or 2P string theory. And this is these people's proposal. And we will focus on P equals to 0 today. And to Hooft coupling, which is as usual, GMU squared times N, has a non-trivial mass dimension 3 in this case. Okay, in 4 dimension, it's dimensionless, but in 1 dimension, it has mass dimension 3. So this coupling constant gives energy scale of the theory. By combining the Hooft coupling and appropriate power energy, we can make a dimensionless combination. And this can be regarded as a sort of a dimensionless effective coupling. Then in this combination, taking lambda large and taking E small is the same thing. You know, this combination becomes large. In that sense, low energy and strong coupling are the same thing here. You may also think that low temperature and strong coupling are the same thing. And actually in the confined phase, that's correct. But we have to be very careful when we try to go to M theory region. Here, instead of temperature, I want to use energy. Okay. And in a gravity side, black D0-brane solution is known. And by using that, they calculated the energy of the black hole. And then it should be 7.4. This is a calculable constant, calculable number, times n squared times this non-trivial power of the Hooft coupling times this non-trivial power of temperature. And because the Hooft coupling has dimension, simple dimensional analysis doesn't work, and very strange power can appear here. Okay, we can always compensate strange dimension by using the Hooft coupling.
I have a question. I have two questions. When you say this theory is is type 2A string theory, blah, 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 do you mean that it's type 2A, that it's a black hole in 2A string theory, or do you mean that it is 2A string theory?
So it's again in BS, as you and the collaborators proposed, various different objects can be described by this model. And here, what we are saying, and probably what Itsuki and the collaborators say, is that if we consider bound state of all these D0-branes, that should be dual to black D0-brane in type 2A. But if we take different configurations, maybe different type 2A in different background may or may not be realized. But at least they are saying that all these D0-branes are forming bound state. If we see such state, then that should be type 2A black D0-brane. And they don't.
Yes, yes, but it's not. But it's not the full type 2A string theory.
It may or may not be in that sense. Yeah. So at least the black D0-brane is described by taking a bound state of.
Okay. All right. So that's what. Let's take that to be what you mean. Okay. Now the other question, maybe you're going to answer it. In which case, I will wait. What do you mean? Who's confined? What confinement are we talking about?
You will see, but energy over n squared goes to 0 at large n. And the Polchinski loop goes to 0 at large n. In that sense, it's large n. So here, to define confinement.
I said confinement. What's confined? Who's confined?
So I would say color degrees of freedom are confined. And also you will I will also show that in a sense, it will become clear later when we introduce geometric interpretation. But you have like a Hagedron string picture of the confinement. That in confined phase, that Hagedron string becomes shorter and shorter and just become graviton gas. In that sense, it's confined. So.
Is there a definition of confinement here that that I'm missing?
Yes, I will give. But you can say that in this theory, the simplest definition is just use a Polyakov loop P to whether it's 0 and the theta symmetry is intact.
Polyakov loop in what space? This is a 0 plus 1 dimension.
0 plus 1 dimension, and so when we do thermodynamics, we take imaginary time, and we compactify temporal circle.
Are you saying that the Lagrange multiplier that enforces gauge invariance has an expectation value?
Yes. And I will explain how that is related to black hole. That is actually the second part of this talk.
Okay.
Yeah, and so in a large n counting, so here, so we take lambda to be 1 and t to be order 1, and then we have n squared here. So whenever t is non-zero, energy is n squared, order n squared. And
Masanori, since I'm new to the subject, is part of the point here that this black hole seems to exist for arbitrarily small temperatures? Like in ADS5 times S5, the black hole doesn't exist for low enough temperatures.
That's a really good point. And here I said any non-zero temperature. But actually, this is n to the 0, but small. So if this t is small but order n to the 0, black hole exists. But if this t becomes like n to the some negative power, then black hole can disappear.
Yeah, that's what I meant. Let's not scale temperature with n, but if temperature is order 1 in n, you say this black hole always exists.
It exists at any non-zero t.
Okay.
And at any non-zero t, energy is n squared. That was mean, and matrices are n by n, So that means all color seems to be visible.
So the potential transition you're going to talk about, the confinement, deconfinement transition, happens at temperatures that are inverse powers of n.
Actually, it's more non-trivial because I want to distinguish energy and temperature very carefully here.
Okay, all right.
So you will see the picture soon. And this, okay, so this is a your gravity prediction, okay? And from now on, I set lambda equals to 1. And if dimension doesn't match, please just supplement some appropriate power lambda. Okay, and Monte Carlo simulation, like lattice gauge QCD, is doable in this theory. And by using very standard lattice gauge theory technique, we can do thermodynamics of this matrix model. And non-zero P are also doable, but there are several technical issues. And one of the most important, probably the most important thing is that we need a lot more points to approximate the Euclideanized space. So if it's just a 0 plus 1 dimensional theory, so we have just imaginary time, and we just introduce the lattice point along imaginary time direction. Okay, but if we have spatial dimensions, we have to introduce points to spatial dimensions as well. And then at large volume, number of points needed to have good approximation quickly increase at a higher dimension. But in 0 plus 1 dimension, we have only one direction, so we don't need too many points. It's almost a stupid thing, but when we do numerical simulation, this scaling is crucial. And thanks to this property, we can go to very large n. Okay, and we can actually take large n limit, which is important in holography. And one subtlety, which hasn't actually developed yet, is a sign problem. If you don't know, you can just ignore. And if you know sign problem, which means a fermion determinant is not necessarily real and positive. Let me just say phase quench, which means instead of using determinant, we use absolute variable determinant, forgetting about complex phase. That is valid empirically. And in some parameter region, we can make a precise argument that why such approximation is correct. And here we used this approximation. And the result seems to be fine. And we consider metastable bound state of all D0-branes. As I already said, and it was a part of important part in a BFSS proposal. But this model can have various different objects. But we want to say we want all D0-branes to form one single bound state. Okay, and we studied that bound state. That bound state is just metastable, but it's a very long lifetime. And we can actually measure the energy of such system.
Wait a minute, why is it metastable and not stable?
So because of flat direction. So
no, I know, but the flat directions, it's supposed to be absolutely stable. It's supposed to be a graviton.
When n is infinite, it becomes more and more stable.
When one is it? When one is it infinite?
When n is infinite. So like a typical time scale for emission of one D0-brane increase like exponential n.
So in the BFSS limit, I think he's saying that in the limit that n goes to infinity, then then the thing is stable. But for finite n.
So
that's not true. It was checked for finite n by Sethi and other people.
So in the zero energy, there is a normalizable bound state, but there's a continuum spectrum as well, right? And at the finite temperature, that flat direction is occasionally picked up.
At finite temperature?
Yeah.
Okay. Yes. The finite temperature is, well, a hydrogen atom is unstable at finite temperature.
Yeah. But the interesting thing here is if n becomes large, and if we take the Hooft limit, then at large n, this metastable state becomes more and more stable, and really completely stable in the large n limit.
Okay.
Yeah. And around 2016, we had access to good supercomputer in Kobe and in Livermore. Livermore is like an hour drive from Stanford. And they were good at that time, but they are computers, so they don't even exist anymore. Both of them are gone in 2019. But at that time, they are really good. And we used them to study this model. And we wanted to take large n and continuum limit for various temperatures. So we had to study various different values of n and the temperature and the lattice size. So we had to study more than 100 parameters. And for each parameter, we used a few hundreds to a few thousand CPUs in parallel. Okay, and these two people who were postdoc in Livermore at the time did a really good job. And this is the result. So this is a plot of energy divided by n squared as a function of temperature. And this line is supergravity, 7.4 times t to the 14/5. And these are the simulation results, large n continuum extrapolation of the simulation result. Okay, and in this case, low temperature is low energy, and which is strong coupling. High temperature is higher energy and weak coupling. Then a lot of string alpha prime corrections appear. So at strong coupling, supergravity should be good approximation. And if we go to low temperature, deviation from this supergravity has to become small. And actually, we can see that these simulation results are these data points are going closer to this supergravity. And this deviation has to be string alpha prime correction if a matrix model actually describes type 2A superstring. Okay, and these two lines are fit obtained by paper before this one. And there was some tension, so we wanted to get the very precise result. But you can forget about these two curves. Let's focus on these points and these lines, okay? And this line is a fit of this simulation result, which take into account the string correction. Okay, and from string theory, we can show that the energy divided by n squared, which is the mass of black hole, should scale like this supergravity result plus alpha prime correction. This is alpha prime to the 3, this is alpha prime to the 5. And we know this number and these powers. analytically, but this overall coefficient is known. And we assume we used these powers as as input, and used kept these three overall coefficient of each power to be fitting parameter. And of course, we wanted to fit this power as well, but if there are too many parameters, fit doesn't work. So we had to do 3-parameter fit. Then this A, whose gravity prediction is 7.41. After fitting the data, we go to 7.3 plus minus 0.3. So they are really good. Agreement is really good. Supergravity seems to be working. And also this power 23/5 is a non-trivial prediction of alpha prime stringy correction. And we wanted to reproduce this. And these two numbers are not known. And if we use both this power and this power as a fitting parameter, there are too many parameters. So string theory tells us this difference of these two powers is 6/5. So we used it as an input. This is a bit of cheating. And we assume the leading supergravity is known. And then we have only 3 fitting parameter. And we could determine this power P. And we got 4.6 plus minus 0.3, which is very close to this power. So it seems that superstring is really reproduced from this matrix model. And now 2 people in Germany, Norbert Bodendorfer and Stratos Patelodis, in a collaboration now, are trying to add a few points here. And the preliminary result agrees with this curve very, very well. So I hope soon we can give more evidence. So please stay tuned. But okay.
Matsunori, I have a question. So the low temperature regime, you said this 14/5 exponent is predicted by supergravity, the black hole.
Yes.
On the other side, if we approach it from the high temperature side, as you're saying, the coupling is very weak. Do you know what the asymptotic behavior is at infinite temperature?
Yes, that can be done using, without using gravity from a matrix model side, we can do such calculation. And that is, of course, reproduced.
How does it look like?
So at asymptotically high temperature, it just becomes a straight line. So it's proportional to temperature times n squared at a very high temperature.
Okay.
And we can estimate first order correction to that. And that's very precisely reproduced.
And can you do, I guess you can't do numerics in that regime.
In that, numerics is easier. At the high temperature, actually, it's harder.
Okay.
No, sorry. Low temperature, it's harder. High temperature is very, very easy. And
okay, so high temperature, you have both numerics and you have the analytical result and they match.
I would say semi-analytic.
Okay. Okay, all right, thank you.
Yes, some numerical calculation is needed, but not it's different kind of numerics, and we can actually check.
Is the slope known in that limit? Is
So,
the slope known?
In that limit, it's like 6 times n squared. So E over n squared is 6 times t or something. It's just it's quantum mechanics. You can just count the number of degrees of freedom.
Yeah, I was just curious whether you could fit a line to your plot there and see whether that slope matches.
You have to go very high. So the highest temperature here is 1 in the unit of the Hooft coupling, and you have to go like 5 times higher temperature. So approach is non-trivial.
I see. So that high temperature is just some equipartition theorem or something.
Yes, just equipartition, exactly. So it seems type 2A is totally fine. And if we believe the duality between type 2A and the matrix model, then we get the deconfined phase, and we get only the confined phase. And I want to make an argument that the confinement should be not really a consequence of the theory. This is speculative, but let me try to convince you to some extent. This is a picture taken from a paper by Susskind and collaborators. And this direction is log n, and this direction is log of E inverse. So this direction is low energy. This direction is large n. And we show the plot from this region. Okay. And this, according to them, this is M3 region. And this region can be related to BFSS proposal. Okay, so oh, I forgot to write it, but this is by using a type 2A black D0-brane solution, we can estimate the value of dilaton at the black hole horizon. Okay, and the dilaton increases as energy goes down. So M3 circle, size of M3 circle should be proportional to string coupling. So string coupling increase would mean that the string coupling increases would mean near the horizon M3 circle gradually opens up, while black hole becomes smaller. Then, of course, we have to, if M3 cycle becomes as large as black hole horizon, then we cannot ignore the effect of 11th dimension. Then, but still, if in this picture, this direction is M3 cycle. So you should identify this line and this line, to compactify. If black hole is not too small, or almost as large as M3 cycle, then it would completely fill 11th dimension, and it looks like a uniform string. And of course, this uniform string has to have a D0-brane charge, which is KK charge in M3. So this is a boosted uniform string according to Hitherto and collaborators. And if you go further low temperature, then black hole shrinks and M3 cycle becomes larger. Then no uniformity appears. And eventually, this black hole cannot fill the M3 cycle, and the black string is pinched off to form a black hole.
Sorry, Masanori, could you remind us what the slopes of these two lines are on this plot?
In the paper, they explain, but I cannot immediately tell. But this is, they estimate where this dilaton becomes large, and then energy should be some negative power of n if this becomes larger than order 1, right? And that is this line, I think. And they have a similar estimate of, so if energy is some negative power of n, then this pinching off should take place.
Could you show that formula again just one more time so I can write it?
Yeah. This is in this paper.
Okay, thank you.
Yeah. But their analysis is also very qualitative because the detail of gravity duality is really hard to tell here. It's not precisely known, and they try to refer to the result by BFSS or paper by Banks, Fischler, Klebanov, Susskind, or Horowitz and Martinek, and then try to determine these values qualitatively. Anyway, so this 11-dimensional black hole localized on M3 cycle is what they call by matrix black holes.
Sorry, could you say again what's the second slope means?
So this line corresponds to the transition from non-uniform black string to black hole. So it's so-called Gregory-Laflamme transition.
So in the region C, it's a uniform string, but in M theory, region where the size is large.
So I'm not really sure if they distinguish non-uniform string and uniform string. This region is both the uniform and the non-uniform string is here. And this is a black hole.
Okay, I see.
Sorry, so maybe I was thinking wrong. Is region B the uniform string and region C the non-uniform string?
No, region B is still type 2A black D0-brane because even if energy is some negative power of n, we can still keep dilaton to be small. Then, so even if we go slightly beyond the Hooft limit and the energy decrease with n, if it doesn't decrease too quickly, we can still keep G string to be small. And we can use type 2A. Okay, so yeah, and yeah, that's so this is still type 2A D0-brane, though energy is decreasing with n along this line. This is a bit non-trivial point. So what is needed in order to use type 2A is alpha prime correction is small and GS correction is small. So the Hooft limit is not mandatory actually. Like for the n equals to 4. As long as you take G squared to be small but order 1, you can still use type 2B supergravity. Okay, but anyways, here I restrict myself to Hooft large limit for simplicity. So we take a T fix, and then energy scales like n squared in the confined phase. And qualitatively, the energy behave like this, as a function of temperature. And if we plot the Polchinski loop, then we get something like this. And this is a prediction from type 2b, and the confinement is taking place at any temperature. But I want to claim there is a confined phase. So at infinite to n, energy is exact zero. So energy can increase at finite temperature, but if energy increase like some small power of n, E over n squared can be zero. Okay, and the Polchinski loop is also very close to zero. And I want to propose that such phase should better exist if we assume M theory is described in the theory. And this phase should be regarded as a confined phase. And more precisely, this is large n picture. But at large but finite n, this free energy minimum, which corresponds to, which is the confined phase and corresponds to type 2a, this cannot continue all the way down to zero temperature. At some point, string correction becomes large, and this phase disappear. And at the same time, there is another confined phase here, but this temperature, highest temperature of this phase cannot go to infinity. This is large but finite value, and there is some free energy maximum separating these free energy minimum in between. And as n goes to large, this temperature goes closer to zero, and this temperature goes up. So this is a bit speculative, but I want to explain why I think this has to be the case. And so this deconfined phase, we already saw that this is type 2a superstring. And I want to claim that this free energy minimum, which is confined phase, and this free energy maximum separating between these two minima should be regarded as M theory phase. And this free energy maximum should be related to 11-dimensional black hole. And in order to explain why I think this picture is natural, let me start with a much better understood example, which is 4D super MLs on 3 sphere, which is dual to type 2p string on ADS5 cross S5. This case is much better understood. And I want to claim that something very similar is happening. First, so assume duality is correct. Okay, and let's do microcanonical thermodynamics in gravity side. By microcanonical, I mean we take E to be controlling parameter, and we fix energy and find the maximum of entropy. So we find a state which maximizes entropy at each fixed energy. Then at very low energy, so where E over n squared is exact zero in large and limit, we have sparse gas of graviton, or sparse gas of short strings. Okay, so here I wrote as if energy is exact zero, but if we take into account one correction, this is gradually going, energy is gradually going up when temperature is increased. And then at some point, so-called hagedron string becomes entropically favored. So those short strings combine to form one long string with complicated shape. Then entropy and energy is proportional to this length, and temperature doesn't change. And if hagedron string becomes sufficiently long, then sufficiently many large entropy and energy is packed in small region, and it should better be treated as a black hole. But this is a Schwarzschild black hole, very small Schwarzschild black hole. Oh, by the way, by this box, I meant the ADS5 cross S5. ADS5 cross S5 is essentially a finite box. So this box is like finite size box, and the size of this box is RADS. Okay, and this black hole is much smaller than length scale of this geometry. So this looks like a 10-dimensional black hole in flat space. Then, like usual Schwarzschild black hole, energy scales like T to the -7. And this n squared is just G Newton. Okay, and interestingly, as energy increases, temperature goes down. Okay, so specific heat is negative. Then at some point, the black hole becomes very large, then completely fills the compact space S5. Okay, so there's a phase transition from a localized black hole, localized on S5, to S5 filling black hole. Then this S5 filling black hole is 5-dimensional in the sense along S5 direction, it's just trivial. So we can focus on ADS5, okay? And then it's ADS5 troubleshoot black hole. And then as the energy grows, at some point, specific heat turns positive. Okay, so this is a well-established gravity picture. First paper is probably Witten's paper in 1998, and there are many good papers after that. And I don't think anybody doubts this phase diagram. And such phase with negative specific heat sounds, kind of a pathological, unstable phase. But small black hole in ADS is actually totally stable in microcanonical ensemble, and such phase can thermodynamically make sense because it's like a object with negative specific heat living in a finite size box. If some graviton is emitted from black hole, then at some point you will, if this original black hole is not too small, you have hot black hole and hot gas in thermal equilibrium. Okay, so it can exist stably. Okay, so it's meaningful. This intermediate phase is meaningful. And on the QFT side, if in non-compact space, if we have such phase with negative specific heat, then part of the volume goes to this free energy, this phase, part of the volume goes to this phase, and two-phase coexistence is realized. But S3 is compact, so whether such two-phase separation takes place or not is a highly dynamical question. And the dual gravity analysis suggests that that doesn't actually happen. Okay, anyway, this is a phase diagram in microcanonical ensemble. And if we go to much stronger coupling, if the Hooft coupling increases faster than this specific power of n, then hydrogen string phase disappears, as suggested by Horwood. And small black hole and graviton gas meets directly here. And this temperature, highest temperature of this small black hole and graviton gas phase, interestingly increase with n. And I want to relate this picture to a canonical ensemble, where temperature is a controlling parameter. In microcanonical ensemble, we fix energy and maximize the entropy, right? And then, so entropy of a typical configuration is the function of energy. And we can determine microcanonical temperature following this standard equation. And then energy and microcanonical temperature related, so we can determine specific heat capacity. And it can be positive or negative, as we have seen. In canonical ensemble, canonical partition function is determined by taking the sum of number of state exponential s times the Boltzmann factor over different values of various values of energy. And energy, value of energy, so and the T is a controlling parameter, and the energy is determined such that this exponential is, this exponent is minimized, or sorry, maximized. That would mean at each fixed temperature, we minimize this free energy. Then, so this is free energy. So if we take a derivative of this free energy with respect to energy, then we get this E becomes 1, and this T is not a function of E. And this derivative of this part becomes 1 over microcanonical temperature. So free energy is extremized when canonical temperature and the microcanonical temperature are the same. And if we take derivative with respect to E once more, then we can see that the maximum of free energy corresponds to negative specific heat in microcanonical ensemble. And the minimum of free energy corresponds to positive specific heat in microcanonical ensemble. So these two phases, so this deconfined phase and this confined phase, has positive specific heat. So in canonical ensemble, along at the fixed temperature, if we change energy, this phase and this phase are free energy minimum. And there is an intermediate phase, which corresponds to small black hole, which maximizes free energy. And in order for tunneling between this phase and this phase to happen, it has to go through this, go beyond this free energy maximum. But the difference of free energy increases with n. So at large n, it becomes harder and harder for the tunneling to take place. So at large n, these two phases stably coexist. And this highest temperature goes to infinity if n is sent to infinity in this very strong coupling region. And this picture already looks very similar to what I proposed for matrix model.
Sorry, Masanori, in the uniform black string and the non-uniform black string that you showed, those are the ones that have negative specific heat for you?
I think so, yes.
Okay.
But that's actually tricky part. And because the geometry is not precisely known, I'm not 100% sure, but I believe that is the case. If it's
so all the three things that you showed in that slide near the bottom, all three of them have negative specific heat.
Yes, that's my guess. But it's a bit non-trivial because it's boosted black hole. If there's no boost, it should have a negative specific heat. With a boost, it's not trivial. But I think negative specific heat is natural.
Okay, thank you.
Yeah. So this I want to say that small black hole and the black string correspond to this phase, as you say. And here, the only difference is that this temperature is not going close to zero, even when we take large n. Okay, this is qualitatively different, but already look kind of similar. And I want to claim that in terms of matrices, it's a large n gauge theory, so we have a matrix degrees of freedom. And in terms of matrix, something very similar is taking place in matrix model and the amino theory. And the small black hole is realized in pretty much same way. I want to claim that. And so that's the reason I want to use this analogy to matrix model. And I noticed only recently, but the paper by Banks, Fischler, Klebanov, and Susskind, at least qualitatively said what I had in mind. Actually, I and Jonathan Morris in mind some time ago. These paper, we didn't realize, but these people already had really nice results. So let me introduce their results first, their proposal first. Okay, so it's a proposal right after 2 years after BFSS. And so they wanted to have 11-dimensional black hole. They wanted to describe 11-dimensional black hole in terms of a matrix model. And their proposal is that, though, if I understand correctly, though matrix is n by n, and there are n D0-branes, only part of D0-brane are participating in small black hole. And other D0-branes are not in a black hole, and maybe it can be like a graviton. And the size of this black hole block is order of entropy, and that can be much smaller than n. And as the black hole evaporates, this block shrinks. Okay, this is their picture, and they gave some qualitative argument showing that this is likely, and at least with some modulo some assumptions, rest mass of a black hole can be reproduced from this picture. And I want to claim this picture holds more generally, including like a small black hole in ADS-554 correspondence. And the BFSS-like geometric interpretation, I have to define what I mean by BFSS-like geometric interpretation. I will define soon. And I think this can work more generally, even in ADS-550 correspondence. Okay. But actually, there is a kind of counter argument for this scenario proposed by Polchinski in 1998 and 1999. And he didn't say it's impossible, but he said at least the naive approach doesn't work and some refinement is needed. And I will explain how we can avoid the problem he found. Okay, and I explain how such picture can actually work. And let's go back to these papers again. These people say the Yamil theory in P spatial plus one time direction can describe type 2 superstring on black P-brane background. And the D0-brane is a 1 plus P dimensional object. And there are 9 minus P transverse directions. And this Yamil theory has 9 minus P scalar fields, and those scalars correspond to this transverse direction. Okay. And in 1995, before gauge gravity appears, we then found that actually Yamil theory can be interpreted as a low energy effective description of a bound state of D-brane and strings. And if matrices are close to almost simultaneously diagonalizable, then diagonal entry can describe location of D-brane. I will explain why this is reasonable, but that's what he found. And say, imagine that 9 minus P1, this I can run from 1 to 9 minus P. Okay, they are almost diagonal, simultaneously diagonal. Then by collecting 1, 1 component, we can get to x1, 1, 1 to x9 minus p, 1, 1. So we can get the vector in R9 minus p. And he said this is the location of first D-brane in this space. And the component can give another vector. This is a location of second D-brane in transverse direction. And there are smaller off-diagonal entries. And he says ij component, ij off-diagonal entry corresponds to string excitation between ith and jth D-branes. So if say x3, 4 is relatively large, that would mean between third and fourth D-branes, a lot of strings are excited. And there is a bunch of evidence for this interpretation. But the one thing easy to understand is mass of the string is correctly reproduced from Yang-Mills. So if the two D-branes are sitting at the point xi and xj, string stretched between them should have a mass proportional to length. But if we take this potential term from Yang-Mills theory and take almost a diagonal background, then off-diagonal entry have this off-diagonal entry have this kind of mass term coming from commutator square. Then this looks like exactly mass proportional to length. And also symmetry enhancement pattern is correct. If all the, so imagine that all matrices are diagonal, and imagine that all eigenvalues are the same. That would mean all D-branes are sitting on top of each other. Then such matrix configuration is UN invariant. But this is exactly what people expect in a system of D-brane and strings. And if N1 D-branes are sitting on top of each other, N2 D-branes are sitting at some other point, and so on, the symmetry is smaller than this, but we should still have this enhanced symmetry. And this is properly reproduced from Yang-Mills. And other than, in addition, we can say supersymmetry agrees, and also like Yang-Mills appear as low energy limit of DB action, and so on and so on. So people accept this picture. And if we introduce some off-diagonal excitations in each bunch of D-branes, we can have non-commutative blocks, and those non-commutative blocks would be extended object, like black hole. And in interpretation by Banks, Fischler, Schenck, and Susskind, these extended object embedded in matrix can interact via these off-diagonal entries, and that reproduces gravity. And this model, so we can say that this is a low energy effective action of the D-brane system, but somewhat mysteriously, this can actually capture gravity as well. This is not trivial part of the BFSS proposal.
By the way, Masanori, just to let you know, we're at the 50-minute mark.
So, okay, so I have to rush. And anyway, so this is a kind of second quantization because many different objects can be encoded if n is large. Okay, and the natural hope would be that in a matrix model, so we have 9 scalars, and so we could get the 9 spatial dimension. And in 4D superMLs, we have 6 scalars, which is described R6. But then that would be R6 is S5 times radial coordinate. And this radial coordinate and the original 4-dimension of QFT can be combined to ADS5. But Polchinski had an argument that such a simple description may not work. Okay, so I will explain his argument, and I explain where he made a mistake. And to understand that actually just considering a matrix model is good enough, so let me consider a matrix model. And existing detail of the action or Hamiltonian isn't important, so forget about fermion. And just for simplicity, I added mass term here, but without mass term, this is just the original BFSS. And this mass term is not very important. So Polchinski's argument is as follows. So let's take a Hooft, in this normalization, in Hooft limit, trace x squared is n squared. This follows only from Hooft counting. Okay, whether you take ground state or whether you consider excited state, it doesn't matter. There is no way to change. Okay, and trace x squared is the sum of n eigenvalues of xi squared. So eigenvalue of xi squared has to be n. Then eigenvalue of xi is square root n. But actually, this square root n is too large compared to the expectation from a gravity side. I will show that in next page. And the commutator square is again just from the Hooft counting, it's n to the 3. And from this, we can say that each 9 matrices are not close to commutative at all. So they cannot be diagonalized. And only when eigenvalue becomes much larger than this square root n, off-diagonal entry can become small. Okay, so so from the origin, distance scale square root n, this is a kind of very highly non-commutative fuzz. Simultaneous eigenvalue doesn't make sense. And even when we go very far from origin, we can make sense of simultaneous eigenvalue, and location equals to eigenvalue can make sense, because otherwise we cannot define eigenvalue. At the string theory point of view, this distance scale square root n corresponds to ADS radius in the case of p equals to 3. And in the case of p equals to 0, 1, 2, this is a region where weakly curved gravity is good. If we go too far away from the origin, alpha prime correction becomes large. So in an interesting parameter region where we would be able to see gravity, we cannot have a simultaneously diagonalized matrix. We cannot make sense of location. That's a puzzle Polchinski raised. And I think this was regarded as almost something which is almost impossible to escape, because we use only generic feature of large n counting. But somewhat mysteriously, one idea popped up in my head in last year during Christmas holiday. And once you understand the answer, you can solve this puzzle within 5 minutes. So let me show how it can be resolved. So this is Hamiltonian. Okay, and with this Hamiltonian, so this P is momentum, this X is coordinate. They are metrics, but they are not just a matrix. Each matrix entry is operator. So it's not really clear, how can you diagonalize operator valued matrix? This is a highly non-trivial problem. And by using a standard basis of n squared UN group, we can have Hermitian operators. This alpha is adjoint index. And x hat and p hat satisfy this canonical commutation relation. Okay, so each matrix is an operator. And each matrix entry has to satisfy Heisenberg uncertainty principle. This is the key. So what I explain from now is that this counting is correct. In the past, people tried to avoid this counting using dynamics, but this counting is correct, and it's not a problem. And actually, this step is wrong. And once we assume this is correct. And let me explain why this is wrong. Okay, I said this, sum of n squared, n eigenvalues is n squared, so each eigenvalue is n. Why is it wrong? Because such matrix is not well defined. Implicit assumption in the past is that, so from here, they assumed there is some matrix X, which is n by n Hermitian matrix, and this is just normal, usual matrix, not the operator valued matrix. And the trace xi squared is n squared. And so usually people have the path integral formalism in mind, but the path integral and operator formalism, we can falsify the argument in a similar manner. So let's focus on operator formalism. In operator formalism, essentially what people assume is that x hat was an operator, so they assumed some coordinate eigenstate. By coordinate eigenstate, I mean for each matrix entry, x hat acting on this gives some matrix. And the people diagonalize this. But such coordinate eigenstate is not low energy state. And low energy state is wave packet. And this is wave packet in R9n squared. Okay, so so there are 9n squared coordinate operators. And in this higher dimensional space, we have to take wave packet. And essentially people are taking some typical point, typical the coordinate eigenstate from that wave packet. But that doesn't make sense. And people took one point and try to diagonalize it. But this is non-trivial superposition. So even if you diagonalize one of energy eigenstate, others are not diagonal at all. And it's just wave packet just moves to some other wave packet. And so the meaning of diagonalization is obscure. It's not well defined. Okay, so such matrix is not uniquely determined. And in a path integral formalism, instead of wave function, you can use a path integral weight, and you can do the same argument. And the physically meaningful matrix obtained from wave packet is center of wave packet. This is how classical notion of location is related to quantum mechanics. But we have to take center of wave packet in this higher dimensional space. So let's use yi, and this alpha runs from 1 to n squared. Okay, so this is the center of wave packet. Then how wave packet transforms under SUN. So operator X transform this way, and eigenstates transform this way. And I will show you actual example. Sorry, it's almost under already. But what we can say is if we have a wave packet centered around some well-defined matrix Y, location changes. So center of wave packet transform like this, but the shape of wave packet doesn't change. And the ground state is just well-localized wave packet. And the distance between the center of wave packet is square root of trace y square in this case. And the ground state is ground state is wave packet centered around y equals 0. And if we take non-zero y, distance between wave packet is this. And as long as this is larger than order 1, there's almost no overlap between wave packet. So resolution is not square root, and resolution is 1.
Professor, I'm confused.
Okay.
Are you talking about the center of mass position?
No, center of wave packet in a higher dimensional space.
Yeah, but there's a difference between the spread of the wave packet in center of mass space or in center of the wave packet space and the size of an object. I mean, you can have a very large object whose uncertainty in position is very, very small. So what are we talking about here? Are we talking about the size of the object, or are we talking about the size of the center of mass wave packet?
So so probably one non-trivial thing, probably which is the source of your confusion, is when we say size of the object. So what I want to claim from now is in a BFSS picture, you say there's some block diagonal configuration, and that describes D0-brane bound state. And you would want to diagonalize each block to see size of bound state, right? But that matrix is this centerable wave packet.
Again, I'm just asking a very simple quantum mechanics question.
Mm-hmm.
Are you talking about the size of the distribution of center of mass positions, or are you talking about the extent of the object? You know,
so when you
a bowling ball has a radius which is very big, but its center of mass position is typically extremely well localized. Which are we talking about now?
No, this is this Y contains the size of the object in that sense, not the center of mass.
Okay.
And I'm saying ground state corresponds to Y equal to 0, and the physical interpretation is all the elements are sitting at the origin, and the no string is excited. Okay, then size is 0. Y equals to 0 corresponds to the size 0, and when Y is a non-trivial thing, then you have to diagonalize Y to determine the size of object. But this Y does not correspond to center of mass.
Okay.
In D0-brane interpretation, it explains the extended object.
Okay.
Yeah. Okay. And here, clearly, I'm using a gauge non-singlet state. And you would say physical state has to be gauge singlet. But actually, we have two equivalent ways of writing a Polchinski function. So if we start with path integral with gauge field, and what we get, and we can use a standard, Feynman's argument to go between path integral and the Hamiltonian formulation. What we get is the trace over extended Hilbert space, which contains the gauge non-singlet states like this. But we have a non-trivial projection operator. So in the case of finite temperature, for example, we cannot really integrate out AT completely. And sorry, we cannot take AT equals to 0 gauge completely. And there is a Polchinski loop which cannot be eliminated. Okay, so this G hat is an operator which corresponds to Polchinski loop. And this Polchinski loop runs all over gauge group. In this case, it's U. And if it's a matrix model, then we have integration over all possible group elements here. And this serves as a projection to singlet operator. And then after projection, we get the trace over gauge invariant Hilbert space. So this and this are equivalent. And in this case, what I'm saying is just states related by gauge transformation should be regarded as the same state, and they shouldn't be counted multiple times. Okay, that's the only difference. Okay, and if we want to have a gauge singlet state, just to consider all possible gauge transformation and take linear combination. This way we can have a one-to-one correspondence of wave packet and such gauge non-singlet state. But this is much easier to understand, so let me use this. And my claim is that, or actually we can, I will explain simple example. Sorry, it's already over, but I think it's an interesting part. As long as this distance is order 1 separated, we can distinguish these two wave packets. So resolution is order 1, not order square root n. So location can make sense all the way down to the center. And the ground state just means y equals to 0. And the simplest example is gauged Gaussian matrix model. So actually, the puzzle Polchinski raised applies to this case as well. In the exact same manner, we can have the same problem here. But in this case, we can solve everything. So we can easily understand what I said. So here, it's a gauge. So we have gauge singlet constraint, but other than that, it's just a bunch of harmonic oscillators. So ground state is just Fock vacuum. So for each oscillator, we take Fock vacuum and we take a tensor product. Then ground state wave function can easily be written like this: exponential of minus trace x squared. And this is it's a localized wave packet around the origin. X equals to 0 for all 9n squared entries. And this is gauge invariant wave packet. You cannot take large eigenvalue from this. And so this is exactly what I meant. The ground state is very localized wave packet around the origin. And generic wave packet, low energy wave packet, in this case is coherent state. So we can shift the center of the wave packet sitting at the origin to each of 9n squared direction. That amounts to applying this operator to ground state. If you also want to introduce non-trivial momentum, you multiply this to ground state. But let's consider Q equals to 0 case for simplicity. Then,
well, I think you're talking about literally translating the system in 9 dimensions. Is that right?
Not the 9 dimension, 9n squared dimension. That's a point.
You're translating in 9n squared dimensions.
Yes, that's a point. So the point, again, when you talk about the geometry, whether you want to talk about R9 or R9n squared, that's confusing part. And first, we have to identify the center of a wave packet in R9n squared.
Okay.
Then after that, we diagonalize and get a geometry in R9. That's a point.
Okay.
Yeah. Okay. Then we can easily see that by gauge transformation, center of wave packet moves this way, but the shape of wave packet doesn't change. It's a very easy exercise. And here, what I'm proposing is we should interpret center of wave packet in R9n squared to be matrix, which appeared in Witten's argument. And I will explain why that has to be the case. Let's see center symmetry and correct symmetry enhancement pattern. So let's take Y, this center of wave packet Y, to be diagonal. Okay, we can take such state. Okay, and let's assume ith D-brane is sitting at this location. Then quantum state centered around such Y is this. Okay, and this quantum state, if y1 to yn1 are the same, and yn plus 1 to yn1 plus n2 to be the same, and so on, this quantum state has this symmetry enhancement. But if you just take one generic coordinate eigenstate from this wave packet, you don't have this symmetry enhancement pattern. So to have this symmetry enhancement pattern, you have to interpret center of wave packet in high dimensional space to be geometry. And if we look at the Higgsing effect, so let's introduce a small coupling term here. Okay, and take this wave packet. Essentially, inserting this or multiplying this operator to ground state would correspond to sandwiching Hamiltonian by this operator and its dagger. But then this x hat is shifted, x hat plus y. Then from this commutator term, you get the correct mass, which is proportional to separation of center of wave packet. And again, if you just take a generic point in wave packet, you don't get this correct Higgsing effect. And so, this center of wave packet is that geometry. And the problem is that the previous argument just took a generic point in wave packet. We had to identify the center. And the generic state is, of course, superposition of wave packet. Okay, so this is how Polchinski's puzzle is resolved. And that example was for free theory. And with the interaction, of course, coherent state may not be good low energy state. And I don't have analytic solution. But the natural construction of the low energy wave packet is that to minimize energy satisfying this constraint. Then the symmetry argument I gave should hold as it is. And I want to claim that actually this, we can see y is, if y can have a state in which y is non-zero here and 0 here, and that corresponds to small black hole. That's what I wanted to say, but I already spent 70 minutes, so I think maybe I should skip this part. In a question time, I can continue, but let me just say, so what I wanted to say from now is that, so this way we can define wave packet, okay? And this y, center of wave packet, is the geometry. And I want to say that in this y can be block diagonal. And that block is an object in BFSS proposal. If we interpret it that way, we can have complete parallel in a proposal by Banks, Fischler, Klebanov, Susskind, and actually something happening in 4-dimensional equals to 4. And in both cases, small black hole is described by this kind of partially deconfined state. And so I have too many slides, sorry, but this kind of picture is holding both in 4D equals to 4 and BFSS. And so I expect qualitatively the same pattern. And I think confined phase has to exist even in BFSS. And in a question time, if you are interested, you can stay and I can explain. And let me skip many things, but I wanted to say that this kind of phase diagram is expected in BFSS. And this intermediate phase is that partially deconfined phase. And in 4D equals to 4, we also have a partially deconfined phase. And if partially deconfined exists as unstable saddle, then confinement phase has to exist. And we actually find such phase. Let's just show numerical result. Okay, so we studied the temperature 0.2 in BFSS matrix model. Okay, and in this case, we studied the temperature n equals to 10, matrix size n equals to 10, 12, and 16. And this L is number of lattice points along the temporal direction. And we took a continuum limit where L is infinite. And at each n, we can see that E over n squared is consistent with 0 in continuum limit. And so if we take continuum and large n, of course, it's consistent with 0. On the other hand, if we use dual type 2A solution corresponding to the deconfined phase, we get something like 0.08. But if error bar is much smaller than 0.08. Okay, so energy is clearly smaller, clearly consistent with 0 rather than the confined phase. And we can also calculate a Polyakov loop. In this case, at each lattice size, if we take large n, we can see that the result is consistent with 0. So again, continuum large n value has to be 0. And if in the confined phase, at the same temperature, actually Polyakov loop should be something like 0.5. And so we can confidently say that the BFSS matrix model has a confined phase. And based on analogy to 4D equals to 4, I wanted to claim that similar, sorry, I prepared too many slides, similar phase like this. Such confined phase exists if a small black hole phase is sitting in between. That was what I wanted to claim. So that's the reason I wanted to claim that finding a confinement phase would mean it's likely that M theory is there. Maybe, so I already spent around 15 minutes. So maybe first we should go to question, and if you guys give me some permission, I can explain the rest, which is also very interesting, I think. I want to explain why such a block structure, small block structure, Banks, Fischler, Klebanov, and Susskind found has to appear. And actually that is related to previously unknown, very close analogy between Bose-Einstein condensation and color confinement at large n.
Okay, I think let's thank Masanori once. And since you spent so much time on this Polchinski argument, I actually didn't quite get what the objection was. So maybe we could discuss that. Like you had this blue, light blue and the dark blue, and
yes.
What was the problem? And
so firstly, if as a ground state or you want to detect, you imagine that you wanted to use the D0-brane probe to probe the geometry in gravity side. Okay. And weakly curved gravity or sub-ADS, if you want to see geometry in that length scale, you need an eigenvalue much smaller than square root n. Okay, but what he was saying that if we go this length scale, already in ground state, matrices have huge non-commutativity. And if we take eigenvalue go into this range, we cannot really remove off-diagonal entries, and we cannot simultaneously diagonalize eigenvalues as simultaneously diagonalize matrices. So we cannot define location. In Witten's interpretation or BFSS interpretation, it's assumed that matrices can be simultaneously diagonalized almost up to small off-diagonal entries. And Joe's argument say that that does not seem to be working here. And furthermore, you would imagine that in ground state, all D-branes would be peacefully sitting, at the origin without any excitation. Because
this problem is specific to p equal to 0 or what? Like, is it also
no, any p. Because here, what I used is just to Hooft counting, and even if you have in here, at each spatial point, this argument holds.
So, but in ADS5, we can. What is the puzzle in ADS5?
So again, because you cannot at each spatial point, non-commutativity is too huge, so you cannot use. So in Fodenian these matrices are sitting at each spatial point, right?
Yeah. And
what I try to claim here is that at each spatial point in R1, R3, R3, I wanted to use this emergent 6-dimensional space to these scalars to have emergent 6-dimensional space at each R3. But the non-commutativity is huge at each spatial point. So at each spatial point, we cannot really construct R6 by using Witten or BFSS interpretation. That was a puzzle. So that's the reason this kind of probe D-brane picture, if you look at Maldacena as a first paper on ADS5 CFT4 correspondence, this kind of picture is mentioned. But because of Joe's argument, people thought that maybe this was too naive. And if we want to use this kind of intuitive picture, some refinement is needed. But I want to claim that some sort of refinement is needed, but that's a very trivial refinement. We just have to carefully distinguish coordinate eigenstate and wave packet. That's my argument.